All right. Well, our first talk is by Michael Grass with Golder and Associates, and he has his long title right there on the presentation slide. So I'll let you read that for yourself. I won't try to read to you. So, Michael.
Hello. Yeah, so I'm going to focus on the geotechnical engineering of monitoring heap leach pads during operational activities, mainly because, um, and using what we call the observational method. So it's originally defined by Dr. Ralph Peck, for earthen construction, which during the operations of leach pads, that's exactly what we're doing, right? We're stacking ore. It should be considered an earthworks, right? And then using this method, it gives us an opportunity to evaluate geotechnical conditions. You could also use it for metallurgical. It's a different set of tests. But during the operations of the facility, to confirm that what the design engineer assumed or estimated at the design phase is actually happening in the heap as you're operating, right? So if it'll turn. So what we're looking at is various data techniques that we can use to collect data on geotechnical conditions. And what are some typical data that we need collected, right? So data from geotechnical field investigations and laboratory investigations. Visual monitoring is probably your most effective type of monitoring that you can do to see how your heap is actually behaving. Pore pressure monitoring over time, and then deformation monitoring. But then the key to that is to feed that data back into the original design models for slope stability and do the two match. Do your new data match the assumptions that were used in design, or do you have a problem, or maybe it's operating better than had originally been predicted? And so you want to take that data, put it back into slope stability models, and then particularly in the work that I do with copper heap leach pads, you'll find out it's not the slope stability model that turns out to be the predictor of behavior or of your heap. It's more the physical conditions you see on the ground and looking at acceptance or performance criteria that you set for the heap will probably predict or run more how you operate the facility than worrying about a safety factor. So what are we looking for in geotechnical investigations? So we really need to see what's going on in the subsurface. One of the issues we've got on the design side is if we're lucky, we might get a ton of ore that we then use in our lab testing in up front. And somehow we're supposed to extrapolate that to millions of tons or hundreds of millions of tons of ore. We're never going to be able to do that. There's never been a sample that would be considered representative of that scale at what we can do in the design phase. So really your heap becomes the experiment. And so then what we need to do is collect samples from the heap at various depths and try and gather samples for laboratory testing. And then do we have zones potentially of high pore pressure that are built up inside the heap? You may not see it, but it could be in there. So things that we can do to identify what's going on inside the heap, like geotechnical drilling, cone penetration testing is a pretty good tool for identifying subsurface conditions. It can also give you pore pressure conditions, material behavior types, a whole variety of things. Test pits for bulk samples at the surface. And then another great one, geophysics, which will let you look at resistivity over a very large distance across your heap, where drill holes are points in space. The geophysics can tend to look at a much wider area and give you a better idea of what the overall scope of conditions are inside your heap. So then as I said, CPT testing can be a very useful technique. Doesn't work very well in ROM. I believe somebody's got a paper using CPT and ROM, so that'd be interesting to see. But usually in crush leach facilities, So it can give you pore pressure conditions, zones of compaction. You can see tip resistance changes to see where you might have zones of high compaction. Soil structure for agglomerated materials, you can see if that's holding up over time. Shear strength, and then behavior types. Is your material behaving like a sand or a clay-like type material? Hopefully we run everything as sand-like, but that's not necessarily how it wants to behave going forward. So our best tool for figuring out what the performance is of the heap is visual monitoring. It's the cheapest one to do as well, and the mine can do it on its own. So we're always looking for signs of change or parts of the heap that change differently than the rest of the heap, right? We're looking for differential change, and can be done by a geotechnical engineer, but we also train the operations team, water balancers on the leaching crew. People in crush convey can also be taught how to look for these signs. So you can go from a team of 1 or 2 geotechnical engineers to a team of 100 folks out there who are out there every day, be able to find things like signs of cracking, seeps. If you have seeps, you actually have pore pressure problems inside your heap. It's guaranteed. Sinkholes, which would be really bad, bulging, some slumps, active slope failures, scarps where failures have previously happened. And another sign is if you do have cloudy solution, you may not see a seep necessarily, but if your PLS or your preg solution starts turning cloudy, there's movement inside of your heap that you may not be seeing, but showing up as piping of fines and coming out in your solution. So most critical to slope stability of a heap is what is the pore pressure condition inside the heap? It's water really that causes the problem, right? If it was all dry, we would never have any problems. I can design a pile of rock to stand up forever under most conditions. Pore pressure changes that, right? So how are we going to measure pore pressure? We can install piezometers, either open standpipes, vibrating wires, or transducers, depending on whether you're manually monitoring things like with an open standpipe or using telemetry to gather more rapid data through like vibrating wires or transducers. Again, geophysical surveys can give you what the breadth of your pore pressure concerns might be. Again, piezometers can only measure a single point, where then you can take that with geophysics and extrapolate that out to the majority of your heap. And then again, visual monitoring of seeps. And then deformation monitoring. So is a part of your heap moving differently than other parts of the heap? If it is, there's a change in conditions inside the heap different than probably what was assumed and could become problematic. So what tools do we have for that? So survey prism, GPS units, again, they're single point locations that you can monitor. If the area is small enough, those work well, or you can put an array of prisms out to cover an area, but still single point measurements. Satellite interferometry, INSAR, is a great tool for you can get deformation measurements over your entire heap at one time to where you can see where different parts of the heap are moving differently and get direct measurements of direction movements. A little bit difficult, but at least the magnitude of movement of your heap. UAV or drone imagery is a great where visual monitoring, where you may not see areas of the pad all the time. You'd have to walk every bench on your heap all the time to be able to see all of it. Doing a UAV or drone survey where you're using video in particular, where you can fly all the way around your facility in a pretty rapid amount of time. You can do a visual inspection of your entire heap in a couple hours. Extensometers, inclinometers and shape arrays can give you the movement at depth. All these other methods only see the surface, right? So how the surface might be moving one way, but in the subsurface, you could be forming failure planes in your heap, and you wouldn't necessarily see it in the surface deformation. So having inclinometers and shape arrays give you that opportunity to see what the subsurface is doing. And then in high seismic areas, having seismographs helping with the evaluation of deformation. So then the next step is taking that data and putting it back into that stability model that had originally been done. Now, this particular model I'm showing here has CPT data, three parts on it, 3 parts of this section, all mapped out with the material behavior type. So sand-like material at the top, transitional, and then the blues are clay-like materials. And then you can get that into your slope geometry, use the geotechnical investigation and lab testing to get you the shear strengths of each of those material types. With that CPT data, we've also got pore pressure measurements. So we can estimate, in this case, there's a perch zone of water above this layer right here, and estimate the pore pressure conditions at that point. We confirm those with piezometers at different elevations within the pad. These piezometers are dry. These have pore pressure measurements in them, so that confirms the CPT data that in fact we do have a perch zone. And with that, we can then come back and calculate a safety factor. And does it match what was originally designed? I doubt seriously that any engineer designed their leach pad with these assumptions in mind, that they had ever enough data to know that their materials were going to behave this way at each location within from top to bottom on that heap, right? Usually they'll assume a homogeneous material and that's it. One material strength, one material type. And yet at the end of the day, it is likely that you're actually getting a condition like this inside of the heap. And most leach pads are designed to assume to be free draining. Makes the math easier for one thing. It's what you hope to have happen. It's not necessarily always going to be true, likely isn't going to be true. And then where would you put the perch layer, or where would you put the pore pressure in your design to begin with? And it's not likely to match that, where you're going to find it out in the future. And so then you can take that and use that model to develop thresholds for pore pressure within your heap, with assigning maximum pore pressure measurements in your piezometers. And then you can adjust your operation of the leach pad so that you don't exceed your factors of safety. But with that, you'll find out that heaps tend to behave anomalously at a very small scale, where you're even your cross sections that you set for as critical sections for slope stability may not be in the right place. That a portion of the pad receives some potentially low strength material in a part of the heap that you don't have instrumentation. So you might see that in your INSAR data, you're seeing excessive rates of movement in an area. You might see a seep that hadn't been identified before crop up in an area. That changes happen fairly rapidly. And that factor of safety does you absolutely no good. Right. And so then what you end up find out that what you develop is through your observations, a series of acceptance criteria. Do you limit the rate of deformation that you're willing to accept on this leach pad? You end up going through the heap and doing effectively a risk assessment as to what you are willing to accept in terms of rates of movement or amount of pore pressure, rates of rise of pore pressure. You might not have exceeded your overall factor of safety in area, but you're getting rapid pore pressure increase. So do you then say, you know what, I'm not going to accept more than a foot per day of pore pressure increase inside my heap? I'm going to then change either irrigation or something else that I'm going to manage on the heap to reduce that rate of rise, rather than waiting for you to exceed a safety factor, right? And or there might be conditions that you see in the field where we've set a limit on our leach pads of a seepage face not more than 4 feet high, because we've got enough experience with that heap that if it gets to 4.5 feet, it's going to cause a bench scale failure. And if you have enough pore pressure built up that behind that seepage face, you end up generating a progressive failure. And then somehow you got to work to get it to stop moving, right? So we actually have a performance criteria where you set the extent of seepage that you're willing to accept. Otherwise, then you have to manage it some other way. The other one is you might have enough seepage that even though you don't exceed safety factor, you might find out that you have incredibly high erosion rates during storm events that then cost you a lot of time and money to go fix later on. So you might say, hey, if the amount of seepage we're seeing in a particular location gets to a certain extent, we're going to cut it off, right? So in fact, I think we actively manage leach pads more off acceptance criteria than we ever do on safety factor. We just don't even want to mess with the safety factor, so we just don't get there. We just manage it based off the conditions we identify in the field. And so with that, then setting up what we call KPIs, key performance indicators, becomes critical. What conditions in the field most affect slope stability? So pore pressure being one of them. But other aspects of operating the facility, fines content, total clay in your ore types that might affect permeability in the future, tracking all of those things, making sure you're within limits on those, and guaranteeing that you don't have a safety factor problem out in the future. That's it. So yeah. So, I mean, the observational method gives you an opportunity to evaluate the performance of your leach pad, and then compare that against the original design of the facility and making sure that they actually match. And if they don't, then gives you a way of learning enough about your leach pad, be able to set performance criteria that you can then actively manage your leach pad with.
Thanks, Michael. Pardon me, but I just want to refer back to Peck's paper that was published in Geotechnique based on the work that Tazagi did. And the big part of the observational approach is not so much the observations, but it's indeed looking at what to observe, have a working hypothesis, then analyze what can happen if you get to the worst set of criteria. You calculate that and you come up beforehand with methods of how you are going to correct that. So you made a list of all the different observations, but it's to me like you need the list of observations and you say, but if we find this is what we will have to do to correct it. We find this is what we will do to correct it in the full application of the observational method. Otherwise, you really just use monitoring to set up the criteria and the KPIs or the TARPs. And so I think I'd recommend that you look at adding that extra piece as well.
Yeah, fair enough. Yeah. So whether you're reducing irrigation on your leach pad to reduce pore pressure, or having to build buttresses to manage pore pressure that's there where someone doesn't want to turn down their irrigation rate, which is the more common case, I'm afraid, or regrading your leach pad or whatever it is you have to do, right? So yes, the mitigation part, it would be the next step. The only problem with mitigation is they're so specific and tends to be site specific. It gets hard to. It is. Yeah, the management part.
Thank you. That's a great talk. Appreciate you coming. Our next speaker, Stephen Slupsky from Scanometrics. He'll be talking about in-heat sensors. Take it away, Stephen.
Thank you very much.
We're here to talk a bit about using sensors to visualize the inner workings of a leach pad. As we are somewhat aware of some of the major problems with leaching ore are your moisture levels that affect the flow. Your metals recovery is affected dramatically from these things, and leaks contribute to productivity loss and environmental compliance issues. So it's been, the literature has shown that there's sort of an optimum level for leaching material based on the literature, and a lot of research that's been done over the years is generally, I think, suggested that 50% saturation is the best amount for leaching. So using your ore porosity calculations, that works out to about a 18.3% volume water by content level of the ore. Using these numbers, we also established that as your compaction increases, it also affects your optimum volume water content of your for your optimum leach as well. So as the compaction increases, your optimum leaching moisture content actually goes down. So what we did is we developed these sensors that get embedded in the leach pad. The sensor itself is put in these little geomembrane sacks. The sacks are dumped into the ore body. They contain a moisture sensor, a temperature sensor. There's a compaction sensor in there to measure the ore pressure and give you an idea of what your relative bulk density is. There's a GPS sensor built into this thing, so when you place it on the leach pad, you've got an idea of its the coordinates of that particular sensor before it's varied. And then they use what's called a distributed sensor array, or a distributed antenna system, to actually get the signals out. So we run horizontal or vertical antennas through the ore to the edge of the leach pad to actually transmit the signals. But the sensor signals themselves are wireless, and they communicate through the air. So that they're intended to monitor moisture and compaction inside the heap. You're making a direct underground measurement with these. They tend to be fairly easy to install. You just take that little sack, create a depression in the ground, and bury them, and then you can backfill over top of them. The more complicated issue is just laying out or planning out how you're going to run these antenna wires, whether or not you're going to run them up the side of the lift, or if you're going to go horizontally out the side of the leach pad. Sampling can be done every minute, every hour. You can set that, and it gives you regular 24/7 daily feedback for control of your leaching process. So if you want to adjust or optimize your flow rates, you can use the data from this to understand where you're getting flow, where you're not getting flow, and to make adjustments to your process as needed. Here's some examples of some of the measurements of the data. The upper graph there shows the moisture measurements. Some of these sensors were decreasing in moisture content. The lower one is actually compaction measurements, and some of those you can see there are sort of step changes happening in the compaction. Those particular ones are during backfill. So you're seeing every time there's more backfill put on the leach pad, you're seeing step changes in the compaction of the sensor. Temperature changes as well over time. You can do a graph of that. You can, using the GPS coordinates of the sensor now, you can map this out to visualize sort of a three-dimensional or a top-down view of the leach pad. So on the left here, we've got an illustration sort of showing a couple segments of sensors going, up and to the right, and then some baseline. Same array of sensors, this time showing the variation in temperature over a 24-hour period, what was going on inside. So when we set out to do this and develop these sensors, we did some work to try to understand how moisture affected the productivity and the production, the gold production. And again, did a lot of this analysis by reading and reviewing the literature, talking to people, but actually conducting some experiments at a mine site, using the sensors, collecting the data from the sensors, and then doing assays on the ore as we were collecting the measurements. And what we found is that early problems are not overcome with time. As many of you know, these are asymptotic relationships, and a lot of times if your leach process starts wrong, you'll never get all the gold out of there again. So getting it right as early as you can is really important. Obviously, the longer in time you stretch out your leaching process, the more energy you're consuming running your process, and the more chemicals you consume. So you've got your operating costs increase. So time is money in heat leaching. Moisture affects gold recovery in time. So again, we did some experiments where we varied the volume. Again, these are our sensor measurements where we're measuring volume water content. We varied that at different rates, but the total amount of solution was the same over the 21 days or 28 days shown in the graph here. And again, you can see if you don't get off to a good start, it makes it very difficult to catch up at a later time. Here's some more graphics showing the performance of an actual in situ sensor, the target being 18.3%, and we can see some sensors are running at a higher moisture level, slightly high. Some are under irrigated or under moisture. We got one, the red one there is about right. The changes you see, the little dips are due to points in time when the irrigation is stopped. So again, you can tell when you lost irrigation. You can tell how long you've lost the irrigation for. You can use that data to anticipate what you have to do to catch up again due to these interruptions. But don't show it in the paper. That's with the proceedings. There's also some further graphs that show the relationship of precipitation on the leach pad and how that affects the sensor as well. So when we did all this work, we asked ourselves the question: how are we going to help operators better produce gold in their mine? And what we learned was that small changes in these sensor measurements, so small changes in the volume water content, can create enormous changes in the productivity of the process. And so a 25% change in water volume water content can result in up to about a 70% change in the production of gold. So our suggestion is that it's really important to monitor moisture within the leach pad. So you get because time is money, you want to know as soon as you possibly can that you've got a problem with your moisture levels and you need to make some sort of take some sort of corrective action. The difficulty in all this, of course, is what is the corrective action, the correct corrective action to do. And even, we struggle with suggesting what to do there. There's lots of information, literature of things people have done to address these issues, like descaling, repairing your irrigation system. Some of these things are obvious. If you've got a problem with the irrigation, you go fix it. It is interesting to point out that how many times visually we would see, when we installed these sensors, we'd see visual indications of problems with the irrigation, but they went unfixed. Like it's like nobody seemed to care that there was, 2 or 3 wobblers not operating or something like that. But when the data started to show that this area was dry because those wobblers weren't running, there seemed to be some more attention paid to the fact that those particular wobblers weren't wobbling. I'm not sure if it's just a training issue, but it certainly helped draw attention to the problem at this particular moment. We've seen in other presentations about ripping the surface, drilling. There are other techniques that they get more expensive to do. Ultimately, you can put a new liner in and address some of the problems with the new liner if you've had sufficient leach or stuff on it. But the outcome we're looking to do, or we get out of all this stuff, is to increase the metal recoveries. The data we've collected from the use of these, clearly shows you can get, and in our pilot sites have shown that you do get more metal. You can reduce your chemicals, your reagents, and your power consumption, and improve and monitor your stability of your even detect leaks in your mine. And that's it.
Well, thank you, Stephen. That was a great talk. And we do have some time for questions if you have any. Yes, and we have a microphone too, if you could speak into the microphone.
Thank you. Nice talk. What is the monitoring volume of your moisture content sensor?
Sorry, I beg your pardon?
What's your monitoring volume? How far out does it see?
So
into the leach or
little sack I showed in the picture there, it's about 12 inches by about 24 inches.
So that's the monitoring sensor,
So
or you
that's the-
fill it with ore?
That would be the sensor cell that would then interface with the ore body around it. The sensitivity of that kind of depends a bit on the structure of the ore around it, but you're going to get a fairly representative representation of that moisture within within I think of 1 to 2 meters kind of thing at that point.
So your monitoring volume is 1 to 2 meters from that?
Yeah. If you have something, if you got water, unless you've got a channel that's that's bypassing or something like that directly affects it. What's happening within a couple meters of that sensor represents pretty accurately what's going on.
Would you mind sharing what the technology of that is? Because the only things that see out that far are different types of frequency, which don't measure water content directly, and a nuclear neutron gauge, neutron probe.
It's a combination of what we use in that sack and the sensors that are actually embedded in there. The sensor material itself is only contained within that sack. But it's the fact that it absorbs from its surroundings that gives it its sort of representation of what's going on. But as I mentioned, if you have a channeling effect that's very, very local, then you're not gonna, that's not gonna be reflected in the sensor.
Okay, so I guess I don't understand. Is it seen outside of the sack, or is water coming into the sack to equilibrate,
Water's flowing through the sack.
with the surrounding? Okay, I get it. Thank you.
Have any more questions? Well, thank you, Stephen. So next up is the esteemed Dr. Jeff Winterton of Victoria Gold, and he will be talking about the Victoria Gold operation.
Good afternoon. So I've been watching guys have struggles with this all day and a little slow on the uptake already, so apologize. But like Dale, thanks for the introduction. Wanted to just talk today a little bit maybe differently than some of the other talks, focus more on the operations. It's really what I enjoy, and they get some unique perspectives that I think we'd like to share. And I haven't gone through this in full length yet, but if I planned it right, I should finish a little bit earlier so we have a little bit more time for questions, because I think this will generate a little bit of interest. So again, talking about process operations at Victoria Gold Corp Eagle Mine. It's a property I've been working with for about almost 3 years now. Starting in 2019, December of 2019. So okay. So just to give a little bit of background, a little bit of overview of the site right here. So we just have a conventional open pit operation, ores hauled to the primary crusher, got a Metso or a Mark II 6550, targeting about 36,000 tons a day through the primary crusher. Primary crusher then feeds a secondary and tertiary crushing operation. It's in closed circuit, targeting a P80 of about 12 millimeters right now. That material is conveyed across a valley over to the heap leach facility, and then use conveyors to stack the material on a conventional valley fill type design. It's leaching operations supported by an ADR plant. It has two 1,000 meters cubed per hour trains flowing across the heap. Average recovery about 98% inside the ADR. And first gold was poured in Q3 of 2019. And since then, it's kind of grown to target around the 200,000 ounce per year mark. So it's a quick summary of the operation. You can see here, it's pretty much a conventional valley fill type design. So you've got the embankment at the bottom there, pregnant solution pumps. You can see the ADR off to the side. So the pregnant solution pumps the ADR. Then the ADR takes the barren solution, pumps it back up. There's two main headers along the east and west side, going up the heap. Then it's redistributed on top using 12-inch and 4-inch drip HDPE down to drip lines. So as of right now, there's about 24 million tons placed on the leach pad with 190,000 meters squared leaching area. The total lined area is just over 580,000. And with a max depth right now of 84, working our way up to a maximum permitted of 130. And it's got an in-heap pond that's just over 58,000 meters cubed. So nothing too fantastic about the design. So why are we talking about it? It's really, in this case, the location. So Victoria Gold's Eagle Mine is located in the center, basically the center of Canada's Yukon Territory. It's 370 kilometers north of the capital city of Whitehorse. The temperature and climate is classified as continental climate, but basically means the temperature there can range from anywhere from plus 25 Celsius in the summertime to getting down into the minus 50 range. So quite a big variation. Average temperature for the year is actually only minus 3 Celsius. And right now it's full on winter there. It snowed like probably a foot since I left last week. And total precipitation we get is on the order of about a meter, with most of that coming in between September and May. So quite a lot of challenges. So the first thing anybody talks about when they talk about leaching up in the far north of Canada is solution temperature, okay? The real takeaway from an operations perspective is uncontrolled flow causes problems. So you can see two guys out on the leach pad. That mountain behind them is not a mountain. That's an ice castle on top of the heap, okay? I've seen ice castles on heaps before, but nothing prepared me for the ones I saw this year. So that, you can see the shape of it is nice, good arc. And that came from an uncontrolled drip line that was allowed to spray. So you can imagine what that would do if we had the whole heap that way. But the caveat to that is controlled flow is totally manageable, right? So in the graph here, let's see if I can get the pointer. You can see that this is the temperature profile, average daily the daily temperature profile since basically the startup of life of mine. And it's very interesting that you can see the seasonal swings that we get right here. And then a couple other things are, notice there's only 3 points on this whole graph where we've actually heated the solution. So this was when the heap was very small and in startup mode, and there was some worried about maybe freezing up. And so they turned the heaters on. We've got just over 12 million BTUs capacity for solution heating. But what we noticed is the solution actually heated up pretty quick, and very shortly, it wasn't necessary to run it. So we were able to turn it off. And you see the seasonality swings where it drops way down here. This is all fresh. This is all meltwater infiltrating the heap. And then the temperature rebounds over the year, going up to just over 9. And you can see this seasonal cycle, and it's actually starting to attenuate right now. And I think in probably 2 more years, the heap will be a constant 6 degrees, no matter what. And it's really interesting because if you dig down into the heap about a meter, 2 meters, you can, that's the temperature, despite what it is outside. So the takeaway from this one is heating is okay, but it's not necessarily needed. Come on. So what is needed? So really, heap leaching up in far north Canada comes down to heap leaching anywhere. All it takes is execute the fundamentals. It should be the key driver of any operation. So when I say fundamentals, ripping, burying the drip lines, getting out, doing planned work on schedule. So you can see all of those aspects of this operation right there. The other key thing is to have survey support. Okay, everything needs to be surveyed in, whether it's lifts, whether it's drip lines, whether it's valves, whether it's everything. It needs to be planned. One of the key takeaways from the panel discussion was what Dan was saying, that we need to operate these things like a mill. We need to you basically go out, you stick to plan, you stack to plan, you leach to plan, you stay on plan. If you do that, what you wind up with is basically in this picture right here. So this is an active leach cell out on the leach pad. You can notice there's the furrows where the drip lines have been laid, but there's absolutely nothing else on that surface that would tell you that's a leach pad. That's what you want to see. Everything has been prepped, controlled, and it's in its place. There's no leaking solution. There's no sprayers. There's no nothing. In the tops of these little furrows, that little bit will be frozen, but in the bottoms right there, they're actually soft, even when it's 40 below out. So you can walk on them. You see, you get an indication that a good solution flow percolating through the heap. Again, execute the fundamentals, planned work on schedule. So the next big thing about heap leaching up north in far north Canada is something that I did not have any appreciation to. So it's freshet. And the definition is up there that we can all read. But basically what it translates to is in 2 weeks in May, or starting in late April to early May, all of this snow that's sitting in the valley on the front of the heap, all of this is going to drain off, melt and drain in a period of about 2 weeks. Okay. So what I'm showing in the graph right here is we have 3 ponds on site. We have the in-heap pond, a control pond, and the event pond. And that's what we use to store water. And you can just see the volume change right here over that 2-week period. You're taking 180,000 cubes of water coming down in the course of 2 weeks, and you have to be able to handle it. Okay. Now that sounds like a lot and it sounds like a challenge, but really it just comes down to planning and management. Okay. The first key thing you can see here, just what I'm talking about. So this is a drain coming off a ditch upstream. That's a full 12-inch HDPE pipe running full flow. That's how fast this stuff comes at you. Okay. So the key to that is like anything else, ditches, sumps. Okay. Try to control that flow. Try to slow it down. Move the water where you need it to go. Don't let it get away. The next thing also that I really didn't have an appreciation for until I lived it is the freeze thaw cycle is real. Okay. Something that might be okay today is going to get wet. It's going to freeze. And then the solution is going to go in different directions. You got to be prepared for it. Okay. It's now standard practice for everything we do. So beyond that, we have all this water that we have to deal with. It really comes down to pump capacity, have the pumps where they need to be, and move that water. Then the most successful way to move water and shed water that I've done or I've found in 20 years is these guys right here. If you need to evaporate water or like basically manage water, slow it down, shed water, these sprinklers are the best method I've ever found. You put them up on a pole, at least 3 feet up. If not, if you can go 10, you get rid of them. So if anybody needs them, they're Seninger Super Spray 500s. They have replaceable nozzles right here. You can dial in the size to basically anything you want to do. These are absolutely key to managing water on a heap. And the next thing is planning. Get ahead of it. Okay. The way to soak up water on a heap is put more ore out there. That's where the water is going to go. So plan ahead. Have some stacked out ore ready to go to be able to absorb that. And then the next thing is we're going to try this next year. So in addition to that 180,000 cubes I mentioned that's coming at the site, we have about another 60 of melt infiltrating in the heap. And that also comes over a period of about 2 weeks. What we're going to try this year is get some of these big agricultural sprinklers, and starting in about mid-April, when the sun comes out and it starts getting warm in the days, we'll put these out and actually melt the snow, drive that melting, pull all that water forward so that when the actual freshet comes, we can absorb the site water as well. So it's really just being able to manage that. So operations on the heap, like I mentioned, not terribly different, just a little bit more challenging. Same goes for the ADR. So inside the ADR, there's no change to the process. Everything works exactly the same. And it's not hard to get 98% recovery in the ADR plant. What is different is you've got to plan ahead. So right here, if you notice, there's an open door right here, and this is a firewater. This heat trace didn't used to be there. you can probably figure out why it needs to be there, right? This is a safety shower. You don't often see heat trace on a safety shower, okay? So this is in the basically the center of a plant. But when it's 50 below outside, the plant gets cold and you need heat trace. Same with carbon transfer lines, right? So the takeaway is if you're going to be operating a plant up in far north Canada or somewhere similar, just spend the money and put in the heat trace. You're going to need it. This thing, it's like, if you click it once, there we go. Okay, so in contrast to the ADR circuit, the crushing circuit, it is significantly impacted by colder weather, okay? In the left picture, you can see this is not a rock. It's a conglomeration of rocks. So they're affectionately dubbed frosties on the site. So you think it's just a collection of conglomerate rock frozen together. It'll take every bit that that guy has with that pick to break that thing up. Okay. So they fall off, they flake off, they get into feeders, they plug everything up. So it's absolutely critical to keep material moving. Okay. If you slow down and get these in the feeder, you basically have to choke off the whole feed, get in, scale it out manually by hand, then take it out. The other thing is scaling. So here's two pictures of scaling operation. So this is the primary crusher dump pocket. You can see how much frozen material is built up. This is actually a little mini X in there that we use to get this out. It's probably about a 2-day operation if this is all frozen to get everything out. And then here's a screen panel on the secondary feed. Those are 4-inch openings that are completely blinded off by fines. So the takeaway on this one is this material will freeze up. You need to have heat in spots to keep this from going. And then just think about the maintenance time, okay? This, having to deal with these types of problems can extend basically maintenance time up to 200% of just the simple tool time, just by virtue of how much material that has to be scaled. Okay. So with that, I kind of finished up a little bit short to allow for some questions.
Have some time for questions. Now, again, I would ask that you use the microphone. Have a question over here.
Thanks for the presentation. Do you see any recovery decreases during winter from the lower solution temperatures?
That's a bit tough to answer. So there's been some, over the past year, we've actually exceeded the production model because I think some ore wasn't getting necessarily wetted. And the biggest recovery impact would be from not wetting the ore because of some flow issue or frozen issue. If it's wet and it's flowing, I don't notice any different on the recovery rates in the extraction of gold.
But have you guys tested, like you say, you don't run your heaters, but have you tested running hotter solution to see if it impacts recovery?
Have not.
Okay, thanks.
What kind of time frame do you run in between having a cell stacked out and then actually installing the drips, especially during the winter time? And do you face any challenges in letting that ore sit there?
There are some challenges. So ideally, and what we focus on coaching the crews up is once the ore is placed, guys need to be on it, ripping it, piping it, and getting it under leach in less than 5 days, right? It needs to be out there and going, and then we'll leave it leaching as long as we can until we have to go stack over it.
Thank you. One more, if no one else is asking. Have you ever experienced any contaminants in your freshet that come in and ruin your ADR plant?
Nothing specifically that ruins the ADR plant. That thing's pretty robust. As far as ruining my day, yeah, there's a couple things that usually show up, but usually it's melted snow. So it's coming down, it's got low hardness, it's got low alkalinity. You're picking up a little bit of suspended solids just from what's coming down. And then there's some organic matter that usually comes in too, because you're just washing the entire hillside essentially at once. So nothing too bad, actually.
Two quick questions for Jeff.
Yeah, damn.
You mentioned they don't really need the solution heaters. Why do you think that is? And also, do they crush and stack during the winter months?
Good questions, all of it. So yes, do crush and stack during the winter. So there was some plans initially to kind of suspend tertiary and secondary crushing. We've proven that we can do it and keep it going all year. Okay. As far as this solution heaters, so I mentioned in that it showed the graph where they get that seasonal variation. So right now it's pretty much dark most of the day up there, but in the middle of July, it's light all day, right? You have sun going directly onto a south facing slope that is basically just absorbing into that thing. And that's what that water is just absorbing all that solar energy, and it just goes up to 10. And then in the winter time, when you're actively leaching, the snow actually is an insulating barrier. And so it might be -50 outside, but the solution's not seeing that -50. It's actually getting insulated from the brutal elements. So. Yeah.
Have you considered recharge wells for getting rid of your water? So they'll protect it?
We have. I'd really like you to come and talk to some people. It creates some challenges. We have some current water issues. We have a little bit too much, and I would really like to get rid of some of it. But yeah, recharge wells would be great.
Thank you, Jeff. That was a great talk. Our next speaker is Sileymane Lo of Cyanco. And welcome.
Thank you, Dale, for this introduction. Today, I will be presenting the use of cyanide analyzers in heap leach operations. As a cyanide supply, oops.
No.
Oh. As cyanide supplier, we know that cyanide is a major operational cost in heap leaching. So online cyanide analyzers are used in mill operations to control cyanide usage, and they have been very effective in controlling cyanide additions. And we believe there is an opportunity to use these cyanide analyzers in heap leach operations to achieve some cost reductions. I will be elaborating on the importance of controlling cyanide additions, brief overview of Cyanco cyanide analyzers, the benefits of using these analyzers, including some case studies to its effectiveness in mill operations, and finally, the opportunity to adopt the similar approach to the heap leach operations. it is very important to optimize the cyanide because it lowers the operating costs, and at the same time, it maximizes the gold recovery. Cyanide concentration can be measured manually or automatically, but manual control of cyanide is slow and tend to be or tend to result often in either overusage, which impact or you have increased operational costs, or underusage, then you have a reduced recovery. Online cyanide analyzers, in the other hand, are faster and they are more accurate. This is a typical setup for cyanide control system. This happened to be one of ours, but the components are almost the same for all the analyzers. You have a filtration system, and you have a sample collection to pump the solution to the analyzer. You have a erection vessel inside for a potentiometric analysis. And then you have your PLC to program and sort the analytical steps. The main benefit of using cyanide analyzers is that they allow higher frequency, more accurate, and more consistent measurement. This graph shows two sections. One on the left, this is before the cyanide analyzer was installed, and you see the fluctuations, the readings are all over the place. And on your right-hand side, this is after we installed the cyanide analyzer. The readings are more stable, and they're closer to the set point, which give you confidence in your result. And when you are confident in your result, you can also lower your set point with confidence, right? So that graph was from a mill. And after the analyzer was installed, the client was able to garner about 10% of saving in cyanide, and then another 10% of saving in detoxification costs. To demonstrate the success of cyanide analyzers in heap leach, let's look at some case studies. Case study number one, the client analyzer was taken down for 4 days for maintenance. And during those 4 days, the cyanide was controlled manually. And the client lost something like $186,000 between increased cyanide consumption and then detox cost. And then the other part of it was the loss in gold recovery. This is evident through the major fluctuation you see in the middle of the graph, the cyanide controlled in this chart here below. The case study number two, the client was having difficulty seeing the titration endpoint. And then they was having challenges also with the time lapse between analysis and the additional rate adjustment. So after the cyanide analyzer was installed, the client was able to make an annual saving of 480,000 in cyanide, and then another 720,000 saving in detox cost. Sorry. There are some challenges in applying or installing the cyanide analyzers in heap leach operations, but with challenges always comes opportunities. And the challenges for installing cyanide analyzers in heap leach operations include the expensive layout of the operations and their remote locations. And the recovery can be delayed if the concentration is below the set point. And there is a difficulty accessing sampling location and addition point. So the fact that the heap leach do not directly benefit from cyanide detoxification, this make the return on investment a little bit challenging. So the objective of this presentation is to demonstrate that cyanide analyzers can be applied successfully in the heap leach operations. Like I said, the heap leach operation do not benefit from detoxification, but they have a big advantage over the mills because most of the time they do not require a filtration system, which is most often a main concern for the mills. Cyanide control is very important in heap leach operations because the result of today's rate may affect outcome many months away. The example below, we will see illustrates different options on how cyanide analyzers can be applied in heap leach operation with many different circuit design. You have the option 1. This is the most common option. The cyanide is added to the barren pump, just next to the suction pipe to the pump. You have here you can. Oh, I'm sorry, isn't there? Here this is the one baseline, the most common one. The cyanide is added to the barren pump next to the section of the pipe to the pump. And here you can have 3 different sampling points. You can sample one from the solution coming from the preg pond, and the other one after the extraction circuit if required. And then the third one that is very important OC that will be after the pump from the solution that go into the heap. And then the result from the analyzer will be sent to your PLC for the cyanide control. Option 2, here the cyanide is added to the pump section. And this is how it's the same similar design like option 1, but this one have a benefit of minimizing the cyanide loss in the pond. You have the third option, which is in case you don't have a pond, you don't have a preg or barren pond, but you have a pump box. So now the cyanide will be just added to the pump box, and this will allow a better mixing. But the sampling point for your analyzers will stay the same. Those 3 positions, 2 of them are the most one or the most recommended one, but there is a third one that is optional. And we have a 4th option, which is in the case you have a copper content, a high copper content. in this one, typically there are two addition point. You can have one at the extraction just before or ahead of the extraction circuit, and then another one can be at the bearing pump, or if you have a pump box, will be at the pump box. In this case also, most of the time, two analyzers are required because depending on the proximity of the sampling point. Now, for the cyanide analyzer to operate successfully, this requires beyond just the design circuit as we've seen. It takes a really rigorous commitment from the management. The management have to be really implicated to make sure these analyzers are used the way they're supposed to be. It also requires a well-trained and dedicated personnel. It requires a defined maintenance schedules executed on a timely manner also. There are also operational consideration, including housing, for example, for the analyzer to protect it from the environment, and then the remote access to be able to access the analyzer remotely for troubleshooting or whatever it is. In summary, the success of cyanide analyzers in mill can be replicated in heap leach operations to deliver mine operation significant cost saving and improved efficiencies. We have demonstrated that significant saving of about $500,000 can be achieved in mill operations. And we believe the same can be achieved in the heap leach operations. In addition, online cyanide analyzers bring ESG benefits, as it can ensure that we do not overdose cyanide unnecessarily. And now presently, we at Cyanco are working on the next generation analyzers with the aim for a simpler, robust, and friendly unit. With that, I thank you.
Thank you. That was a great talk, and we do have some time for questions. We have a question.
You said you use a potentiometric endpoint for the titration.
Yes.
Did you look at other endpoints before you picked that, or how'd you end up with that?
No, the cyanide analyzer, they have two methods, two main methods, either potentiometric or amperometric. This is the setup for the analyzer itself. You don't look in for it, but the analyzer is set up to do that because you use electrode, silver titrate electrode to measure your cyanide concentration using the mill ball. It's a design, it's a construction, it's a part of the analyzer.
Any more questions? I have a quick question.
Yeah.
Is this something that Cyanco has developed?
There are a lot of suppliers. There are a lot of suppliers out there that supply those analyzers. But we at Cyanco, we work with our client. We kind of design this polymetry analyzer to fit their need. but there are not just, we are not making analyze, we're not fabricating, but we are like just a supplier, but we work with other suppliers also. But we are the intermediary because we know each side what they need. So we give them some parameters to fabricate that unit for us. And then we give it to customer.
Another round of applause. Thanks. That's great.
Okay.
All right, so we're going to wrap up this session with a virtual talk by Jeymy Huamanyauri. I am sure I butchered that name, with Andes. Is Jeymy on the line with us right now?
Yes, I
Perfect,
am.
I see him. All right, well, take it away.
It's okay. Can you hear me? Can you hear me? Yes. Good afternoon. In this opportunity, it's an honor to explain about changes in water management during Hippie's lifetime in heavy rainfall sites. For Hippie Solution 2022. About introduction, in this slide, I can show a project where I can opportunity to participate almost 5 years ago. Yes, is located in the eastern of Anderson. Is a typical Hiplish path located in between creeks, in this case creek 1 and creek 2. You can see in this picture the final conformation or final stage or final phases. About the production, it started in 2016. Nowadays, it is operating too, but the production is increasing year by year. About the water management, I could explain in the next slides, but about a summary, this is conformed by perimeter channels in the boundary of the path, heat leach path. Then is connected by rapids until sedimentation ponds located in the low zone in the toe of the heap leach path. About the problematic, in Peru, there are two important seasons: the dry season from April to October, and the wet season from November to March. But according to the government meteorological agency in Peru called Tsunami, the rainfall in Andes Peruvian can present torrential rains any years. This is dangerous because the rainy days or extreme rainfall can present every 4 years, every 7 years, every 10 years is a complex behavior. But what's happened with the heat leach pads? During intermediate phases, if the water management is incomplete or is not completed, so flooding, erosion, and potential instabilities generate worse consequence and insignificant economic losses for the operator. In this picture, I can show the final phases of typical heap leach pads in Peruvians operator, where you can see in the left side the civil geometric conformation, and in the right side you can see the water management for the final phases conformed or made up by perimeter channels connected by rapids and until the ponds, sediment ponds located in the creek. The water management is okay during the final phase. But what happened during the initial phase and intermediate phase? You can see the area, the initial phases, and the intermediate phases is different to the final phase. There are a big area that wasn't considered in the final design. So this area can be destroyed or damaged in the operation zone. For this reason, this paper can be recommended and some kind of methods that I can apply during during the wars in 5 years ago in this Paxol heap leach pad, not here, but another case, but similar. In this paper, I choose the typical heap leach pad. So, yes, in Peru, the tile engineering studies in Peru can be accepted by the final phase. But in the intermediate or initial phases is not made detailed. So it is complete during the operation or made planning for year by year until no, before of the initial of operation. Because the heap leach pads grow takes some or several years later. Meanwhile, the operation of the mining is working on an annual basis according to the operation schedule. For example, in this picture, you can see the short temporal channel located in the perimeter of the heap leach pad. It's a consequence of heavy rainfall sites like Andes of Peru. Changes in water management of a heap leach pad. You can consider some change in water management of a heap leach pad during the preliminary works, cleaning and grubbing, foundation, excavation, under drain, grading, and installation of the liner system. Also, a stage or intermediate phase. because the perimeter of the operation zone is very far of the final phase. And complementary construction or building such as access, platform, and ducts. In this picture, I explain the preliminary works located in the cribs, no? Like cleaning and growing. Next, the under drains, no? And next the grading for foundation, and the final linear system of heap leach pad. It, in some in all cases the rainfall was damaged the operation zone because remember that there are consider a big area that wasn't considered for the final design. Then how it can remediate for a good operation. This item was recollected by experience of Andes and me. For example, update of hydrological information, knowledge of restriction due to geotechnical conditions, limitation of permits, for example, authorized water discharge sites, and timely and schedule planning, including integration between specialists and mine reviewers. It is important because the political of the operator is different in different in different system and different operator to obey a different governance. For update hydrological criteria resume, you need to update the meteorological dates and compare with local station. Most of operators have a local station in the mining in the operation zone because it is to update easily to the information of meteorological dates. The risk of the level of temporary drainage work is the same of the permanent structure, approximately 18%. But the use is different, not 10 years, only 2 or 3 years. It was necessary to modify perimeter channel for intermediate situation. In this case, maintains 10 years of standard, the design stage, so that any interior overflow can be duly intercepted by temporary channels. Yeah. Planning integration between specialists and mine reviewers. About civil planning, request update site information from the operator, like topography, soil classification, geodynamic risk, and as-built drawings. Another is to make an annual plan to water management for operation zones. Consider that the design is different to build. For this reason, maintain to 20% of contingencies of capex. It's recommended to use temporary liner for channel and hydraulic structures like HDPE geomembrane that can easy to use and easy to retire. about hydraulic planning. Evaluate the new runoff contribution. Designs the design can contain the capture most of the water possible. The most hydrolyzation is the trapezoidal. For design about the slopes, the number of fruit can be minor of 1 to avoid high velocities and another dissipation points. Always to control the sediments for ponds located in plain zones, and it permits 10% of the total capacity. And finally, the water management must have constant repairs and cleaning to prevent the flow is interrupted. About conclusions, this paper solve and prevent surface runoff without generating delays in the leach path construction schedule and economic losses during operation. The construction of heap leach pads in areas of intense rainfall needs updating the water management plan annually during the intermediate passes for operation of the heap leach pads. Also, according of Andes experience, especially during first years of operation, the impact surface runoff of heap leach pads is manifested in flooding in operation area and instability of existing access due to the action of weather flows and instability induced by the coast slope and due for infiltrations. The impact generated by surface runoff can be reduced through the coordinated participation of the site engineer of the site with the planning, design and construction of the mine operation areas to design execute the water management planning in the site in the shortest time possible. According to in the case of the students in this paper, it is known that the cost of temporary linear using the one that 5 millimeters each DPE geomembrane for water management system corresponding to 50% of the cost of permanent linear like a stone masonry. In heavy rail sites, the water management of heap leach pads should be updated annually before the wet season. Also, design for each construction phases for avoiding issues presented in this paper. Thank you very much.
Thank you very much. Thank you for the talk. That was great. We do have time for a question if anyone has a question. Jeymy? Anyone? Bueller? Anyone? All right. Well, I think that wraps up our session. I appreciate everybody coming and listening to the great talks. And I think there's going to be some activities in the next room over. So thanks.